Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm glad to introduce Eli Shechtman from Weizmann Institute. Eli did his BA in Tel Aviv University, and then he started his PhD with Michal Irani in the Weizmann Institute, and he's now finishing, and hopefully he'll be coming to this area, and we might get a chance to be with him more. He did a lot of interesting works, and he won quite a few prizes. And now he's going to talk about from local to global visual similarity in space and in time.
Thanks, Yoni. So, hi, I'm Eli, and I'm going to talk about several problems or recent problems I've been doing during my PhD. And all these problems that I'm going to present are related somehow to some complex notion of similarity between images, videos. Now let's see, what do I mean? So for example, we have this small image of a garden of flowers, and you can see probably a heart made of these flowers inside. And we're interested to find all similar objects within, for example, these images, a data set of other images, where probably you can see that there are quite substantial differences in appearance between the object. And we would like to find all instances of similar objects and retrieve all images containing this heart. Now, a somewhat related problem is in video, where we can be given a small video sequence of some action performed by somebody. And we're also given a data set of video sequences, larger one, longer video sequences containing these kind of scenes, quite complex one with some unstructured dynamics of the background, other people performing other stuff. And of course, the people dress differently, they walk a bit differently. And we would like to cope with all these differences, both in images and in video. Now, the common thing to these two examples is that we are only given a single example of what we're searching for. So we cannot do any learning here. We cannot model any informative parameters. We don't have any prior examples. We only got one single example. And so we'd like to use all available information within this example in order to perform these kind of tasks. Now, in other cases, we could have, instead of a real example, only a simple hand sketch of what we're searching for, and would still want to cope with these kinds of problems. And in a more extreme case, we could have even a task where we don't have any example of what we're searching for. So for example, in this case, we're given a video sequence, and we would like to remove this umbrella. And actually, we don't have any external example of what we want to put behind this umbrella. But I hope you can see that for us, human observers, this is quite an easy task. We just look what happened in other regions of this video sequence, and we can imagine what happened behind this umbrella. And in this work, we would like to do this thing automatically. So our approach would be, since we cannot learn or model anything, we'd like to use all available information within the input data. And in all the example problems that I will introduce, we're going to break the visual data into small patches, 2D patches in images or space-time patches in video sequences. And we'll search for local similarities within and across the visual data in order to obtain some more global similarity between objects or actions in video sequence, and for the completion problem as well. So this is the general approach. Now for the first example problem called space-time behavior-based correlation. This is a joint work with my advisor, Michal Irani, from CVPR 05. So in this example, we are given a short video clip of just a few steps of this walking lady. And we're given a longer sequence, as you have already seen in the introduction, of several other people performing different actions. You can see also the unstructured motion of the water in the fountains. And we'd like to, as done commonly in images, we'd like to correlate this short video clip across this longer video, the larger one, and to find all locations of high behavioral similarity between the actions. Now, of course, we cannot use the intensity or colors there or edges because these are not the same. People dress differently. And however, what makes these actions actually similar is the fact that their underlying motion fields are the same or very similar. So we would like to be able to match these motion fields. However, we would like to do it without any computation of optical flow or motion, and directly from the colors or intensities of those sequences. And this is kind of result that we would expect from the algorithm, where you can see a whole correlation volume of the result. So each pixel in the output gets some value. Here, color-coded with these red to blue colors. And we show it only above some threshold in this case. And these are the highest peaks of behavioral correlation within this larger video sequence. So let's see how we do these kinds of things. We represent the video sequence as a space-time volume. And the same about the short video clip, the template that we have. And we'd like to correlate this video template across the larger video sequence. And in each point, we would like to extract a small video segment of the size of the template and to check the behavioral correlation between the two video segments. Now, of course, the intensities or color patterns between these two segments are completely different. However, we would like to determine whether these two different space-time intensity patterns could have resulted from the same underlying motion field. And we'd like to do it without any optical flow estimation, because this problem could be not well defined or sometimes ill-posed, and without doing any segmentation or any background subtraction, since, as you can see here, the background can be highly dynamic, and sometimes segmentation can be a very hard task. So instead, what we do is we break those two segments into small space-time patches, typically 7 by 7 by 3, but this is not really important as long as they are small enough. And we'll try to compute the local motion consistency between pairs of matching small patches between these two video segments. Now, finally, we will compute the global behavioral correlation as simply a sum or a weighted sum of those local contributions of pairs of patches. So what do I see by motion? What do I mean by motion consistency between small space-time patches? So consider, for example, the following four small patches that they all have different intensity patterns, and they also seem to have different motions. However, due to the aperture problem, we cannot actually observe that their underlying global motion can be the same global motion. Therefore, we would like our algorithm to tell us that these four patches could have been resulted from the same underlying global motion. Where, for example, these four patches, there is no way that they could have been resulted from the same global motion. This is just an example of one such global motion possible for these patches. And therefore, we would like our algorithm to tell us that these four patches are actually inconsistent. So let's see how we do that. So consider our video sequence, and for example, in this case, we have several moving objects in our scene. Now, when these objects are moving in the scene, they actually induce a brush of color lines within this space-time volume. Now, these color lines could be quite complex and quite wild in the real scenarios, real dynamic scenarios. However, we will assume that locally these color lines are actually a brush of straight lines. So we assume this linearity assumption locally in small space-time patches. So we have these straight lines of intensity or colors, and we'll denote by U the direction of the motion, or actually the direction of those lines in space-time. So it has three coordinates, x, y, and t. And we'll denote by a gradient of pi the space-time gradients within this small space-time patch. So those gradients are actually perpendicular to the direction of motion, and this is very similar to images where spatial gradients are perpendicular to the direction of edges. So exactly the same thing happens in video sequences. So if we have this relation of orthogonality, we can just simply stack all those equations into one system of equation, as you can see on the left. Homogeneous set of equations where this matrix is of size n by 3, where n is the number of pixels within this small space-time patch. And geometrically, what it means is that the space-time gradients are actually forming a 2D plane in this case, and U is simply the normal to this plane spanned by those gradients. So we'll denote this matrix of space-time gradients by G, and therefore we get this homogeneous equation, G times U is 0. Now remember that we actually want to compare two small such space-time patches, the motion of two patches. So we actually get two such linear equations. Now if we had to compute the optical flow in those patches, and then only compare the motions, so we would have to compute or solve these two equations, and this is known to be a hard problem in quite many cases of degenerate patches and so forth and so forth. So we would, in this work, we would not solve these two equations, and what we'll do instead, we'll simply have to check whether there exists a U that actually satisfies both these equations without solving them. So we can quite easily do it by simply stacking those linear equations one on top of the other. And what it means geometrically is that we are searching for a U which will be the normal to both planes spanned by the gradients of those two space-time patches. So next, just for convenience, we will multiply this matrix by its transpose, and we'll obtain a new matrix called M12, and this and a new linear equation M12 times U is 0, where this M12 is actually the Gram matrix of G1 on top of G2. It has the following structure. It's a 3 by 3 symmetric matrix, positive definite. And it has actually been used quite extensively in motion analysis and for extracting space-time interest points. However, in this work, we'll use this matrix a bit in a bit different manner. So let's see what we do. So remember that if the two patches are actually motion consistent, they have a U which solves them. So the null space of this matrix M12 is not empty, and therefore the rank of this matrix is less or equal to 2. And if the rank of this matrix is 3, so these space-time patches are actually motion inconsistent, because there is no U that solves both of them, and therefore they are not consistent. So just to summarize, what did we have till now? We had two small space-time patches. We computed simple space-time derivatives within those patches. We stacked them into this joint matrix M12, and we obtained a simple rank-based constraint saying that if the rank is 3, the patches are inconsistent, and if it's less than that, they are consistent. And all this without computing any motion, without segmentation. Okay, now what we find out actually is that this rank 3 inconsistency constraint is a sufficient but not a necessary condition. And what do I mean? For example, we have these two space-time patches. Each one of them, the rank of each one of them is only 1, because in this case we have a whole 2D plane of possible motions for each one of them. However, these two 2D planes are actually intersecting in one line. So therefore, in this case, the rank of the joint matrix will be 2. So we can see a simple example of these degenerate patches where the rank of the matrix is 2. However, these are, of course, inconsistent patches, and they do not obey this rule that we obtained earlier. So we have to now generalize actually the previous rank 3 inconsistency constraint to treat both degenerate and non-degenerate patches. Now let's see how we do that. For that, we'll define the upper left 2 by 2 matrix or 2 by 2 minor of this large matrix by M12 star. And this M12 star is quite a known matrix from optical flow estimation, Harris corners. And it actually captures the 2D spatial structure of those two patches. So what we show in the paper is actually that these two patches, P1 and P2, are consistent if and only if the ranks of the large matrix and the small one are exactly the same. And if they are not the same, so the patches are inconsistent. And this is actually a generalized version of the previously rank 3 constraint that I showed before. So in other words, if we define the rank increase between the smaller matrix and the larger one, the difference between the ranks, to be delta R, so if this delta R is 0, so they are consistent, and if it's 1, the patches are inconsistent. Now, this is quite a hard constraint, and of course, in real life, we have noise, and two patches could be roughly similar, but not exactly the same. So we would like a more continuous notion of this consistency of motion. And for that, again, we show in the paper that we actually managed to obtain this kind of more continuous measure based on the interlacing property of eigenvalues of such symmetric matrices. And I'm not going to show all the math, but this is quite an easy measure. It is between 0 and 1, as we wanted to. It is actually invariant to the contrast of those patches. It has no parameters. We don't have to put threshold on the eigenvalues, actually, in this case. It's a completely continuous measure. And actually, it can be also efficiently approximated using simple determinants of those two matrices and their norm, and actually without computing any eigenvalue in this case. So just to summarize, what did we do till now? We assumed some linearity of small space-time patches, and we computed their motion consistency. However, in large template, such as this one, of course, the motions can be quite complex and non-linear. So what we'll do, we'll compute all pairs of such consistency measures between all matching patches between these two segments. And we'll simply sum them up or do some kind of a weighted sum. Again, more details can be found in the paper. But this is the basic idea, coming from integrating local motion consistencies into one global behavioral correlation measure. If you have some questions before the results, I'll be happy to answer. Yeah?
Is there a scale issue in these?
Yeah, so currently, this method is not invariant to big, large scale differences between the templates, and also not in rotation. However, I'll show in a minute that it is quite robust to about 10–20% of different scales, simply because the motion fields are much more smoother than the texture or the spatial features on of the appearance. Therefore, you can get this kind of robustness. But yes.
The scale question: is there you're doing derivatives in time and space? Is there a scale parameter between the two of those?
No, actually, simple derivatives. Well, you do.
Like they're kind of different units, though, really. But like if you're building a correlation matrix.
So. No, it doesn't really matter, because what only matters is that this assumption that the direction of motion in space-time will be perpendicular to those space-time gradients. So as long as you define this vector in space-time to be with the ratio of 1 between space and time, so it doesn't really matter.
So if you took two motions and just made one twice as fast as the other exact same motion and just sped it up.
So they will not be consistent, because these will not be two parallel vectors in space-time. Maybe this answers your question.
Yeah, I mean, it seems like there's an if you're taking a derivatives in time and in space, you're sort of implicitly normalizing by like one sample spacing, right? Which is like 1 pixel or 1 second, or like Michael's now saying.
Right.
So in the video, what does that mean? It just means you sort of change the sample spacing.
So it will simply be a transform of coordinates. But what matters is what Michael said, that if you have two different velocities of objects, so you will not get the same vector in space-time. It doesn't matter what is the ratio between space and time. What matters is that you don't get the same vector, and this will be inconsistent in our case. So this is also not fully invariant to differences in speed. For example, because of this property. So if you want to extend it to large variations in speed, well, sometimes you don't want to do it. But if you do want to, you have to search in a scale space or things like that. And this is, of course, doable.
How do you determine your template size? You said you had this little kind of cliplet, this small little.
You can see it, for example.
Where the person is. Or
no, but
like
it does have to be quite tightly related to the action. So in this case, if you take a few steps of a person, so you have to have this template quite tightly bounded to the shape of the person, and you don't want to take too many regions outside, because then the template will include many static regions, and you will influence the template.
So if you had the video that you're trying to match this against, if it had a moving background, and the background here wouldn't correspond with that background, is that an issue?
So yeah, that's an issue. If you don't have a static background, and your template does have a static background, so this could be a problem. Yeah. So you can put a mask on top of the person, not an accurate mask, but just a moving rectangle, and we did it in some cases. Yeah, this will help.
And just to clarify, when you actually run this algorithm, are you then taking this template and then trying it at every position in every place and time exhaustively, essentially?
Yeah, so actually we of course do not do that, and actually in this for this example, for this kind of template, and and this kind of video sequence, it ran almost in real time. So what we actually do, we don't compute every pixel. We compute it on a space-time grid of a grid of pixels, and we also do it in multiscale fashion. We start from a lower resolution of both the template and the video sequence, and we end up with several candidate locations, and then we refine the search around these locations. So it's a bit faster than a simple exhaustive. So as you can see here, the background is quite dynamic. There are some other people doing other stuff here. Again, we do not compute any motion here, do not do any segmentation, and in this example we detect all instances of walking people, and we used, of course, in this case, both the direction of actions to cope with both direction of walking.
Why isn't the static part of the background firing higher here? Because the majority of your template is just static.
So again, why?
Because your template, the majority of your template is just a static motion.
Right. So
right?
I think in this case we did use some rough mask around the person. So,
But in general,
but
I mean, it seems like static. Sort of want to rule out static stuff somehow.
yeah. So if most of your template will be static, you will find all static regions within the sequence. So you have to define what you're looking for. It depends on what you define simply. So in this case, since this is not a very dynamic background, and since the static part is quite small or comparative to the dynamic part, so the dynamic part wins in this case, and we find. But it really depends on what do you take as your template. So here is a bit more challenging example of this ballet turn, of this ballet dancer. Now we took this clip and we correlated it against a larger video clip. As you can see here, containing two dancers. One is a female and one is a male dancer. Of course, they have different appearances and different scales, and they perform differently the same type of an action. And in this case, almost all instances of this action were detected correctly, except for two missed detections. Yes?
Is that because it's fast motion and it's only shooting at 30 hertz, and the differences is.
So
or is it-
why we did not detect the hollow? Well, I will show you this example with a different algorithm where we do detect all instances. So one of the problems is that this is a simple template correlation. So it is limited to very large differences. So for example, in the cases that it did not detect the woman, were due to the fact that she was too small and relative to this template. So but other instances it did detect it. So about 20% or 15% of scale are allowable. And she also
the
has.
scale. It's not the fact that the camera times, the shutter times are 1/60th of a second off from each other.
No, not because of that. No. Okay, so now another example. We took this swimmer head diving into the pool. Here's another time. And we correlated this clip against a larger video clip containing all kinds of non-rigid motions. The water here moves unstructurally. There are lots of movements of the other swimmers. And as you can see here, most of the jumping people were detected correctly. Now, of course, this is also a very degraded video sequences. It has lots of compression artifacts. We just downloaded it from the official site of the Olympic Games in Greece. There was one false alarm, you could probably see. And of course, I think computing optical flow on this sequence would be very challenging. And we do it without computing the flow. And again, all instances of these jumping persons was detected correctly, despite of some differences in scale, and they wear different clothes a bit. Okay, so this is for this example. Now in the last one, we can see 5 different short clips of 4 people doing some actions. Here it is again, and one unstructured motion of this fountain. And we took a longer video sequence containing the same people, but this time each one of them performs a different task, a different action. And here below we denote by those space-time ellipses each one of them matching templates. And as you can see here, all instances of these actions were detected correctly, including these 3 unstructured motions of the fountain, water in the fountain. Yeah, so this was about detecting actions in video sequences now while being invariant to appearance changes. Now in this work done with Michal Irani, and we have just submitted it to CVPR, we wanted to do something similar with images. We wanted to be invariant to the appearance of objects. And of course we do not have motions here, so we have to do something else. So consider, for example, these 4 images of a heart in the upper row and these 2 peace symbols below. So in this case, I hope you can see that there are quite some substantial differences between those instances of the same object. And these objects actually do not share any local properties, not the same texture, not the same color. The edges are, of course, different in these cases. However, for us as humans, it's quite an easy task to see that these are actually similar objects. And what is common to these 4 objects above and 2 below is the fact that their local layout of geometric layout of these small image patterns are actually very similar. Or we call it that there is a self-similarity of local image patterns, although the image patterns themselves are not shared across those images. So let's see, what do I mean? So for example, we take a small 1 pixel in such an image, and we take a small patch around this pixel, and we simply correlate it against this larger blue region, typically 80 by 80 pixels, quite a large region around this patch. And using a simple SSD correlation, we obtain this kind of correlation surface. We do, of course, some normalization, and we take the exponent, and we obtain this correlation surface where the highest values are regions which are more similar to this central patch. And then what we do is we subsample this correlation surface in a log polar coordinate system, where we want to be more robust to changes in location in farther away regions from the center, and then regions which are closer to the center, similarly to what was done in shape context descriptors, if you know this work. So additionally, what we do, we take the maximum value inside each of these log polar cells, so to be robust to small shifts within each one of those cells. So finally, we take these maximum values and we stack them in this feature vector. So we obtain a feature descriptor that actually captures this property of local self-similarity of image patterns. Now let's see what can we do with these type of descriptors. For example, we take these two images, and we take 3 patches in the upper image, and the corresponding 3 patches denoted here by 1, 2, and 3 in the lower image. They are located on similar locations across these 2 images. And of course, although the patterns across these images are completely different, there's no similar color, texture, whatever, the descriptors at matching locations are actually quite similar across these 2 images. And we use this property in order to match these kind of challenging images. And let's see what we can do. So actually, SSD surfaces is not something we invented. It is used in motion analysis and clustering segmenting textures and detecting symmetries. Now, in our case, what gives the power, well, this is a powerful tool for us, for our purpose, since it gives us a way to treat uniformly different kinds of image patterns. Now, what do I mean? For example, here we can see that it can treat quite easily those repetitive patterns that we have already seen. We can actually treat also textured regions. We could detect them quite easily using this simple patch-based SSD surfaces. And we can detect regions of homogeneous color. And actually, we can also detect self-similarity of edges up to some extent of orientation differences, as you can see here. So let me just summarize the benefits of these kinds of descriptors. So we obtain some robustness to small local affine and other non-rigid deformations. This gives us a uniform treatment of various complex regions, such as color regions, textured regions, edges, repetitive patterns, etc. And actually, what this descriptor captures is the local self-similarity of meaningful image patterns. And this notion of co-occurrence or self-similarity is also not new in computer vision. It has been used, for example, in mutual information, where the assumption is that similar intensities or similar colors are located at similar locations between 2 images, and that's what enables them to do alignment. Now, the difference between this method and, for example, mutual information is that in mutual information, there is a global description of these co-occurrences, while we are using local descriptions, so we are more robust to some geometric variations between the objects. And also, we are using patches, so we can deal with much more complex image patterns, as you saw, texture, color, as opposed to simple intensities in pixels, which are quite limited. So let me show you how we compare actually such images using those descriptors. So we take a small image template containing this flower, and we take another larger image that may or may not contain similar flowers. In this case, we can see some. And what we do is we compute these self-similarity descriptors in a dense grid within the template and as well within the larger image. Then we filter out some non-informative descriptors that include the salient patches, which have very low self-similarity around them, and also homogeneous regions, homogeneous color, homogeneous texture, which have very large self-similarity everywhere. And we are left with some smaller set with the more informative features, and for them we build a simple star graph model in order to account for similarity of descriptors as well as their geometric layout, while allowing some flexibility. Now we use this graph star model, and we actually compute the log likelihood score for each one of those pixels within the larger image to be the center of the object, or the center of this star graph model. And therefore we obtain a whole surface of log likelihood values for this image. Now we also combine several such surfaces for several scales, since self-similarity can appear in several resolution scales. And we finally obtain this kind of results, where we put a simple threshold on the final log likelihood surface and obtain this kind of a result of the detected flowers. So this is the result for this image, and here are several other images. Some of them contain real or painted flowers, and they also have different shapes, well, to some extent. And these are kind of results we obtained using our algorithm on these images. You can see that the appearance of the flowers are not the same or quite different, and still we can detect these kind of flowers. Now to a bit more complex objects like these hearts. So here are some example of images that we can take or download from the web. And these are the results which we obtained for these images. Now we can actually use several different other image templates as the thing that we're searching for, and we actually obtained very similar results for all these cases. Now we did a more quantitative experiment. We actually did a comparison with other common matching methods. So here is another example of a template and an image. This is our result, and we compared against actually 7 different other methods. Here we show the 3 best of them. So one of them contains extended SIFT features, which are a log polar version of the common SIFT feature, extracted at edge points, and we took them at several scales. We made this comparison as fair as possible. And for the SIFT features, we got this kind of result. We also tested against shape context features that are based on binary edges using simple edge detector. And actually, we used here the code of Mikolajczyk and Schmidt that compared different appearance-based features. And we also compared against mutual information, both in color and in grayscale. And this is the best result we could obtain. You can see that the heart is not quite detected using those methods. Now we actually took 60 such pairs of images containing different flowers, hearts, peace symbols, and other objects. And for these challenging pairs of images, we got 86% of detection, and the best of all other methods was not above 50% of detection. So, okay, this is for this comparison. Now, another possible application is face detection. We didn't actually explore it very thoroughly. We just tested on several examples. So we took this template of Jean-Luc Picard, and we correlated against this image of the Star Trek crew, and we got this kind of result. And actually, we can take a simple sketch of a face and obtain quite similar results also for this simple sketch. And next, we took one step further this idea of retrieval by sketching. We took more complex templates or sketches of templates of human poses, in this case, this kind of sketch. And we took these images as our test images, and these are the results that we obtained. Now, note several things. So first, for example, for this guy, he has, in this case, purple hands, and his body is black. So actually, we don't have a full self-similarity, which is compatible to our template. However, due to this local property of the self-similarity that we use, so it's enough to have good several regions of local self-similarity in order to obtain a good global score for this kind of an image, and also for this guy over here. Now, also note that this guy here was not detected, since we are not totally invariant to scale and rotation. However, this lady over here and this one over here were detected, so we are robust to some kind of scale variations, again about 20% in this case. Look also for the high clutter for this lady with the background. And all these results were obtained using the same threshold for all these images. Now this is another example of a different pose. Note, for example, the high clutter for this in this image, and also in this one. Here the edges are quite weak, almost indistinguishable, and still we are able to detect it again with the same threshold for all these images. Now we did a more quantitative experiment using 8 such human poses, some of them containing 2 persons and some of them 1. And we took 72 real images containing different human poses, where each one of those template poses was contained in at least 8 or 9 even images out of this database. And here is the result for the first pose that we get, where we ordered the images by their global rank of self-similarity. So the upper one got the highest rank, and the lower one, the lowest rank. So also note again the high clutter over here. That's actually a textured clown, or I don't know, dancer over there. And here we mark by this red frame a false alarm. Now actually you can probably guess why it was detected as false. So the upper part of this person was quite similar to our template, and the lower part was, well, there is this fence over here, which might look as legs for this guy. And here's another result for the second pose. So in some of the images we have other people like this one and like this. And here is another one containing 2 people, one on top of the other. So in this case, all these were detected correctly, and we have 2 false alarms over there. And here are some results for the other poses as well. So in all these 8 input poses, we got all 5 first retrieved images correct, and a few mistakes in the lower ranks. Well, note also the high clutter for this lady over here. And that's all about images. Now we can actually take exactly the same idea of detecting self-similarity and apply it in video. Yeah.
Before you go on,
of course.
When you compute your descriptor, do you have to basically you take your local patch around that pixel, and then you have to say how does it correlate with all the other patches around it? Do you do that in an exhaustive way? What's the computation on this look like?
Yeah, so actually we do it quite exhaustively currently, and the implementation in MATLAB, and it works quite slow, about a minute for a big image. But actually you can compute all those SSD surfaces much faster if you do it at once. If you do not compute for each patch its region, and then the next patch its region, but you can instead compute all shifts at once, and then just do a global shift, and this way you can do it much faster.
And you use like a distance transform then to do we had that star graph.
Right.
Do you use it?
No, that's a simple technique of voting. So you just use Gaussian that vote for the center of the object, and places which have many votes will be higher than places with fewer votes. That's a pretty standard technique. So in video, actually, this idea of similarity is much more intuitive, since people do not tend to change their clothes between frames. So there is much more self-similarity, which is more natural in video sequences. So what do we do in video? We take this video, we again represented it as a space-time volume. We take a small space-time patch, correlate it against a larger space-time region, obtain a correlation volume, very similar to the image case. And in this case, we do a log-log polar subsampling, where we, again, give more priority or more weight to frames which are closer to the central frame than frames that are farther away. So in order to obtain some robustness to different speeds and accelerations. And finally, we obtain this, again, a feature vector, in this case a bit longer, 120 entries, and the previous one was about 80 entries. And we do the same thing for detecting actions in video sequences. So we actually tried the same this method on the same video example that we saw before. We took this template of the ballet dancer, and we correlated against the same video sequence. Actually, not the same. We took a longer version of the previously shown video sequence, where you can see here a comparison between the two methods. So this is the previous method, the behavioral correlation. This one is based on self-similarities. So I hope you could see that this one had 4 false alarms denoted here by the red crosses and 2 misdetections. And this one detected all instances correctly without any false alarm. And the reasons, well, we think that the reasons are due to this more flexible treatment of actions in the self-similarity, due to this log polar representation of the descriptors. And we also use a flexible star graph model, so we're much more robust to small geometric deformations between the actions than the previous method that was simply based on templates. And actually, when using self-similarities, we're also not restricted to small motions, as we assumed in the previous method, where we assumed this linearity for small space-time patches. Here, when we use SSD surfaces, actually we can capture very large motions, as long as they are captured by the extent of this SSD volume. So this is for the previous example. Yeah. Now we took several, or actually 2 small space-time templates of these turning ice skaters, and these are quite fast motions using a very low frame rate video sequence. And we correlated them against a larger video sequence containing, this is actually Michal Irani doing some exercises for her performance in the last Winter Olympic Games. And here is an example of detection. Here is the other template. And actually there is another turn over here that is not detected because it's a different one. So we got all instances of these templates detected correctly in this case. And this is a very low frame rate video sequence. So we actually use this fact that we do not need small motions here. Okay, so this was the case where we had one example of what we're searching for. Now, as I told you in the beginning, there are cases or there are tasks where we don't have any external example of what we're searching for. So in this case, this is a work done with Yoni over here and with Michal Irani, and this is quite an old work from CVPR or 4, where the task was to eliminate or remove this lady in blue. And again, we don't have any external information of what we want to put in, but instead we would like to use all available information within the same video sequence in order to do this task. So we would like to use other instances of, for example, this girl in red in order to complete the information. And of course, we want to do it automatically without any user help. So what we're going to do, again, we'll represent the video sequence as a space-time volume, a nicer visualization in this case, courtesy by Yoni. And we mark the hole or the region which we want to remove as this white region over here. And well, typically this is a much larger region than used in image completion method. So the problem here is much more difficult. We can also we cannot also assume smoothness of edges or all kinds of heuristics which were done in image completion methods, since there is large motion in video sequences and things are moving quite fast from frame to frame. So we cannot use any smoothness assumptions, and we will have to do something else. So in this case, as opposed to many previous image completion methods that were based on some heuristic of order of filling in pixels from outside regions to the inner side regions. So in video, these methods will not work, since they will probably, most probably lead to some inconsistent completion of the missing information. So instead, in this work, we pose the problem of completion as a global optimization problem. And we define the global objective function, denoted here by the coherence of H given D, where H is all the pixels within the hole, and D is the dataset region or all other regions outside the hole. And we'll denote by pk 1 pixel inside the hole, and by wk a small spacetime patch around this hole. And we'll also denote by xk the most similar patch outside the hole, which is most similar to the patch inside. So this is xk. Now we define this global coherence function as simply the product of all those similarities of patches inside the hole to their most similar patch outside the hole. And the intuition behind this function is, since we have here a product, so we actually require that all local patches within the hole would be similar to some other regions outside the hole. And we hope that if we have local similarity everywhere, so the global solution will be also coherent or also look quite natural. And this is, in any case, our assumption in this work. And it worked quite good in real examples. So now what we want to do is, of course, to maximize this global coherence function. So we do it by representing this problem as a graphical model, and we solve it using a variant of the RDM method. I will not go into more deep details. I'll just show you the intuitive explanation of this algorithm. So we take a small region inside this hole, or containing some boundaries as well, and we take 1 pixel inside the hole and a small patch around this pixel. Now in video sequences, this is a space-time patch, as we saw in the other methods that I showed before. And actually what we do, we search, we take this patch, we search the most similar patch outside the hole. And once we find this most similar patch, we take the color that is located in the matching location to be our vote, in this case, for the color of the pixel that we're interested in. And now note that this pixel is actually participating in many other patches around this region. Actually, for a 5x5 pixel, there are 125 such overlapping patches. And for each one of them, we search for its matching patch, and we obtain another vote for the color of this pixel, and another one, and another one. So finally, we obtained 125 possible colors for this pixel. And then this was the E step of the EM algorithm. In the F step, what we want to do is to estimate the most probable color for this pixel from all this available information, or for this probability density in the space of RGB in this case. So the most simple thing to do is to simply take a mean or a weighted mean of all those colors, while where the weights are defined by the similarities of those pairs of patches. Now in this work, we found that a more better solution can be obtained if we do a mode estimation, or we do clustering, and we take the the mean color of the largest cluster of all these colors. So we use simple mean shift for this task, and then we obtain much more sharper results than taking just simply the mean. So let me just summarize. We take a pixel inside the hole. We take several candidate patches for this, which give us candidate colors. For this pixel, we, in the M step, take some the mean color of the maximal cluster, or the largest cluster. And then we fill in all those pixels inside and continue iterating the whole process until the convergence of this global objective function that I introduced earlier. And actually, we do the entire process in multiscale when we take the original video sequence with the whole, and we subsample it both in space and in time using a space-time Gaussian pyramid. So the lady runs a bit faster in the end because we also subsample in time. So what we do, we start with some initial guess, simple interpolation. We refine the solution, then we upscale, continue refining until convergence, continue upscaling until we reach the final original resolution of the video sequence. And this is kind of result that we obtain in the end. So now for some results. So this is the sequence that I've been showing from the beginning. You can see both the dynamic parts, this jumping lady, and the static parts, the grass, are filled in a natural or pleasant to the eye way. And in the second example, we actually removed this umbrella, and in this case, both the background and the foreground are dynamic, and I think both of them are filled in quite naturally. In the next example, we took maybe a more important application of removing stains or scratches from all the footage. In this case, we implanted a big stain on this Charlie Chaplin figure, and below you can see the result in the matching frame using the same, exactly the same algorithm. Now, in the next example, you can see another important application where we actually can complete entire frame, or in this case, 3 missing frames in this video sequence. So this often happens in 6 minutes. Great. So this often happens in when you capture video sequences in camera. So you have some drop frames, and you can use exactly the same algorithm for this purpose. And in a final, the last example, you can see that we removed this running lady over there. So in this case, the mask was a dynamic one, a moving mask. And again, both the waves and the other lady were completed. You can approach the screen if you like. Yeah, or I can show you the results later. Yeah, so this is the result for this case. And actually, you can take this exactly the same method and apply it also for images. It's even an easier task. So we use 2D patches instead of 3D patches, and we use images instead of sequences. So in this case, we wanted to remove this bungee jumper over here. And actually, we compare for this case, our result to Cremonesi's result from 2003, where the method of Cremonesi used some kind of a heuristic assumption of giving more priority to pixels which are located on edges which are perpendicular to the boundary of the whole. So he has this kind of a priority of ordering of the filling in process, and so this heuristic actually may lead to giving some priority or bias towards linear edges or straight lines. You can see the leaks of the bushes over here, and maybe the roof over here. And that's it. So we have several other examples in the paper if you're interested. Now, just to summarize what we have seen, so actually we used here the same approach for several different problems. So in the first one, we saw how we can use local motion consistencies across video sequences in order to obtain a global behavioral similarity. In the second example, we saw how we can use local similarities or self-similarities within the same visual entity, images or video sequences, in order to obtain global similarity for these kind of challenging objects or even sketches of an object. And in the last example, we saw how we can use local similarities within the same visual entity, in this case a video, in order to obtain a globally coherent completion of space-time holes or holes in images. And that's all. If you have questions, I'll be happy to answer. And if not, I'll call Henry. Henry?